welcome back. We were, talking about linear regression. So what we have done so far is we just, talked about some visualization of linear regression in a very simple case with only one input variable, and then we have considered a motivating example to see what is a good model, what is a bad model, and how parameters could be estimated, right, from a practical point of view, including measuring the confidence interval of the parameters, right, because these are the parameters that actually determine how good your model is, right. Okay, and then we mentioned briefly that this whole thing of finding a good fit is nothing but solving a least square optimization problem. Okay, all right, and there we have a loss function, and then as we move towards a multivariate simple in a linear regression model, we, instead of a scalar loss function, we are actually a vectorized loss function. Okay, we have a bunch of parameters theta naught to theta n. Okay, so this is the idea. So the question is, how do we do it? Okay, so it's like this. Your loss function, because since everything depends on how good your parameters are estimated, right? So therefore your loss function is actually a function of all your parameters, right? Okay, so in higher dimensions, how does it look? It looks like a soup bowl, isn't it? So it's like this. Of course, it can be very, very nasty, but in this particular case, your loss function is really nice. We can have very nasty loss functions with a bunch of plateaus, and you can deal with have to deal with the local minima. You hit the rock bottom multiple times. But anyway, those are all occupational hazards per se. But as of now, this is a very nice loss function. So if you think about this, it's like you have a ball at one top corner of a soup bowl, right? Some sort of a small ring or a marble, right? And you drop it down. So what will happen is, because the marble will want to be in its lowest energy position, right? But you gave it some kinetic energy, right? Okay, you gave it some kinetic energy. It also has some potential energy because it is falling through some height, right? So what will happen is, since what it wants to be in its minimum energy position, right? So, but how does it figure out computationally speaking? So it will start dropping, right? So you can think of this as an iterative process. With every passing time step, it drops further, right? Okay, and also you can think of it in the following way. If you really do the experiment, right, if you give it enough initial momentum with a lot of thrust, right, it will drop, come down, but it will not settle at the bottom, which is the minimum energy position, right? It will go up and then again come down. It will go up, again come down, go up. It sort of moves, and after assuming there is no friction and other things, right, it will move in a periodic fashion, right, and finally settle down. Now the question is, when does it settle down and why does it settle down? It settles down when it figures out that between two successive iterations, two successive change in position of the vector itself, right, there is not much difference. Okay, so what you are trying to do is you are trying to emulate the descent of a particle. Okay, all right, and when you descend the particle, you compute. So you descend the particle by along the soup bowl, you can keep drawing multiple tangents in different points, right? Okay, now at the lowest point here, what will happen? At the lowest point, your tangent line will be parallel to the x-axis, right, or the weight axis, right? And this is where your lowest point, because you cannot go down any further from both directions. Okay, and that will be, this is a cost function, right, and that will be your global cost minima. So this is a gradient descent process that you employ on your loss function, and you figure out where your gradient is the minimum. And what is your gradient? Gradient is the rate of change of position of the particle along the tangential line, isn't it? From a simple calculus point of view. Well, there are a bunch of issues. Your particle may keep jumping around, but at least in this case it doesn't. Okay, at least in this case it doesn't. So what exactly is the gradient descent? Look, at every, let me go back to that bowl example, right? I mean, let's say this is the position of the particle, right? And then you are coming down, okay? All right. So in every time step, you are iterating and your step numbers will be updated, right? So you would have a gradient update. I mean, in the sense of position, it will be updated, okay? So how that update is calculated? The update is calculated in the following manner. So theta j is a position, okay, of the theta at the jth time step, and it is nothing but when you compute the gradient of your loss function with respect to the parameters multiplied by a learning rate, okay. Okay, all right. And why is there a minus sign? The minus sign is because you are actually coming down. Okay, instead of coming down, if it's a hill climbing problem, on the other hand, if you're climbing a hill, it will be a gradient ascent problem, and the minus sign will be replaced by plus. Okay, so at every time step, you change the theta, right? So because your learning rate is constant though, right? But the gradient is changing, right? Okay, as and when you are moving closer, the gradient is changing, and so that theta will be updated, right? So why do we need this parameter alpha? Because I mean, I really do not want a very large slide, okay? I mean, I don't want an abrupt slide. So I sort of want the particle to follow a trajectory. So if it follows a trajectory in a smooth, nice fashion, I would want to control the amount of descent. It is with that specific purpose, you multiply the Jacobian, the gradient of it, with a learning rate. And typically the learning rate is set is equal to 0.1 or 0.01 or whatever. Now, with this in mind, let's see how we can figure out the actual gradient of the loss function that we are talking about, okay. The squared loss is a standard loss that is used in regression, okay. And you will see this is a case of maximum likelihood estimation because you are estimating the parameter theta, okay. All right. Now what we do is simple enough, right? I mean, we know what is your j of theta, correct? Your j of theta we have already decided. Let's go back. Your j of theta is this. You see that, right? So in the gradient update, you would just plug this in, okay? All right. Now let's just minimize this. How do we minimize this? Because simple enough, I mean, the first step is just the partial derivative, but you know, because the partial derivative and the summation operators both are continuous operators, you can exchange. So you can push the partial derivative inside, right? And we also know that your h is nothing but, I mean, h is a function of theta. It's like theta naught plus theta 1 x1 plus theta 2 x2 blah blah blah, right? Okay, all right. And you have indices of I from 1 to m and index of j from 1 to n, if you recall. Okay, so basically when you do that partial derivative, it's a chain rule. So you take care of the square first, and this is the reason that 2 was brought in with that m. So that 2 and these 2 cancels out, right? And then the second part of the chain is when you differentiate this guy, right? Now what is this guy? This guy is nothing but, as I said, h is nothing but this minus yi, right? So when you are differentiating with respect to thetas, right, and none of the thetas are squares, so these are all linears, right? When you are differentiating with respect to thetas, all you are left with are the coefficients. That's all, okay? All right. So you have this guy times the coefficients, because please note this yi, the last yi here, is a constant. Okay, this is because this is data dependent. So when you take the derivative, it goes away. Okay, all right. Okay, so what do we have here now? Because remember, let us go back to the gradient update step, right? We needed to know this. Okay, all right. So now that we have found this, we can come back and update the step, which is what we exactly do. So now our gradient update for this particular loss function is this. If you change your loss function, which is what you keep on doing in neural networks, right? I mean, this update rule will change. Okay. Please note that gradient descent method is a very, very powerful optimization method, not only used in regression models, but also used everywhere else. Okay. All right. So, and assuming that all the data is available to at one shot, right? You can implement batch gradient descent. Okay. Because you can just simply parallelize this. So I have some example here with a Python implementation. You can just go through this with all the codes, right? Well, one of the sometimes gradient descent, because if your function is really sort of sketchy with a lot of global minima, a lot of plateaus and all, the gradient descent, there is, it can get stuck, right, in a local minima point of view, and so that's something that we should try to avoid. Okay, all right. The other thing that I wanted to talk about is feature scaling. Okay, sometimes what will happen is, since we are talking about a linear regression model with a bunch of input parameters, right? You have x1, x2, x3, and x4. Now, all the values of all these features may not be uniformly scaled. Okay, so some values may be like between 0 and 1, some values be minus 300 to plus 500, so on and so forth, right? If there is so much disparity in the values of the input features, it sort of impacts the output. So what we do here is we do a feature scaling. What is a feature scaling? We can do a z-score normalization, which means we can bring everything to between 0 and 1. We have already seen examples of z-score normalization, right? Or what we can do is we can maximize, you can pick up the maximum value in that particular column and divide every data point or every observation by that maximum value. Okay, all right. One of the problems with z-score normalization is, you are implicitly assuming that your data corresponding to that particular feature follow a Gaussian distribution intrinsically. Okay, if it indeed does, there is no problem in doing a z-score normalization. Otherwise, what you are doing is you are, changing the shape of the distribution. Okay, which is not advisable. Now, as I said, one of the issues of linear regression, or for that matter, please also know that the issues linear regression or regression models face are the issues that most other machine learning models face. So it's not like something that we should be too rattled about. The idea is like for once the overfitting or the underfitting or absence of presence of outliers or presence of some variables, input variables which are not really required, and it will confuse the regression model. Okay, all right. However, also in our excessive greed of trying to have a better fit model, we sometimes compromise on the validation accuracy as well. Okay, so in order to avoid that, what we have here is pretty much as the example that I gave you. If the shape of your data is cubic, what are we going to do? Or for the worse, you don't really know the shape of your data. What are you going to do? If from a scatter plot you know that the data is approximately linear or it's approximately quadratic, it's fine. But if the shape is irregular, okay, trying to find a regression model which will fit most of the data points in that irregular shape becomes a nightmare, in the sense that you may do a very reasonable job on the training data, but the performance of the test data would be horrible. Okay, so one of the remedies proposed toward that direction is actually use weights and hyperparameters to tune your regression model in small local neighborhoods. So like if you can do a very good job on the overall data distribution, at least do a reasonably good job in locally clustered neighborhoods. Okay, so this is known as a locally weighted linear regression model. Okay, all right. What we typically do is we give weights to training data in such a way that when we are trying to make a prediction in that neighborhood, we are close enough. Okay, all right. Okay, so you see here the blue dots are the training data. Okay, all right, and we have a test point. Okay, and we sort of want to predict the value of y. And you can see the way this line is aligned. Fitting one regression model is kind of, right? So let's use the weighting concept here. Okay, because we still want to use that linearization model, right? So instead of looking at the whole curve, we only focus on the curve that are chosen, say 1, 2, 3, 4. Now the reason why it is done in such a way that, look, if I just choose these 4 blue lines or blue dots, what will happen is I am probably still able to fit a line. You can see that, right? I'm still probably able to fit a line, and then draw sort of a local neighborhood embedding, and from the center or the focus, right? I mean, this is my test data point. From the center or the focus, I'm still not too far away. Okay, all right. So how are you going to do this? I mean, mathematically speaking, because we know that the multiple linear regression model has the standard formulation that I have the only parameter that is responsible in fitting the line is theta. In this case, it's not. I mean, your thetas are not the sole parameters, right? So we start with the basic one, which is, we know instead of writing theta naught plus theta 1x plus theta 2x2 blah 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 blah, we write a vectorized representation. Okay, this is basically an inner product of theta and x. Okay, fine. Okay. Now, so this is basically a standard linear regression model. Okay. Now, what we do is, and for a standard linear regression model, we know the loss function. Okay. This is common knowledge, right? Okay. We know the loss function. Also, please know that, since we are not using thetas to fit, okay, and thetas are parameters, right? So regression is a parametric model. Since we are not using thetas to fit, in fact, we are actually using hyperparameters to tune our model for that particular test prediction in a particular local neighborhood. The locally weighted regression model is a non-parametric version of its big brother. Okay, so what we do here is we simply weight the losses, by multiplying with a weight vector in that neighborhood. Okay, all right. So because this weight vector determines how close the test point is to each of the training data points. Okay, and such a measure, distance measure, is known as a kernel measure. We'll see this kernel measure trick in support vector machines later on. Okay, all right. So, and one of the most popular kernels is the Gaussian kernel, for the obvious reasons that it follows a nice exponential decay expression and all that, right? Okay. So let's look at this kernel. Okay. All right. So what do you see in this kernel? You can see that this is exactly what we want, because what we want points which are close to the data point, right? When that's the case, xi minus xi. Right? I mean, this is a negative function, right? Exponential. And when this is smaller, the weights are larger, right? And when xi minus x becomes large, right? Which means your test data point is not close enough to the local neighborhood, right? Okay. Then what happens is, if this is large, because of the minus sign and the exponential, because it's a decay function, the weights become smaller. Okay. So basically, based on the weights, we determine whether a test data point is close enough to the prediction that we want to do. It's very, very simple. Okay, it's just a very, very clever kernel trick. Okay, now what is the effect of this weight? The effect of the weight is that, I mean, everything else is same, right? Xi is your training point, x is the test point, and then we have a new parameter, right? And this new parameter is, right, this is a hyperparameter. Okay, and this is something that you choose. We choose this. The model doesn't learn this, right? Now, based on, as you can see, right? I mean, if the hyperparameter tau is large, more data points are considered. If the hyperparameter tau is small, a smaller number of data points are considered. So, meaning that basically, the implication of this is that the test data point, if the tau is small, the test data point will be in a very small local neighborhood. Okay, for the prediction. However, if the tau is large, it gives you more freedom for the test data point to be predicted. And the Gaussian kernel actually gives us the fundamental idea that closer you are to the data point, the weight will be close to 1. Further you are to the test data point, the weight will be close to 0. Okay, all right. So, I mean, I'm not going to go through the proof, but if you use the loss function, which is a minor tweak of this, okay, basically what you will end up getting is something like this. Okay, now let me tell you, in regression without the weight parameter, I mean, we are not talking about the locally weighted linear regression here, we are only talking about the linear regression, this W thing is missing. So the way to estimate parameters by using a matrix vector notation is, if I don't have the locally weight tuning, then I will have the value of theta as x transpose x inverse times x transpose y. This is in fact known as the pseudo inverse. Okay, I'll tell you why this is the case in a linear regression model. I mean, we just so that you are not lost, and because we haven't used this before. So you know that, I mean as you have seen in SVD and APC and all the other things, you are I mean your information matrix is usually rectangular, right? Which means, I mean, you have pretty much, I'm dealing with a problem like this. Okay, all right. Now this guy A is not square. Probably I should be using y just to be consistent. Okay. So this theta is where you hold all the parameters, right? Yeah, that you would want to estimate, right? Okay. So let's just go back, look at the this thing, right? So I have to estimate theta, right? Now the question is, I typically, from a linear system, right, ideally I should have x inverse y, isn't it? Right? But this is not the case. This is not the case because your x matrix, your input matrix, input data matrix, is also not square. Okay, so what we do is multiply both sides by x transpose, right? Okay, and if you do that, you make this square, of course, and then of course, I mean, you'd have to estimate theta, right? So you know you can do this x transpose times x transpose inverse, and so you do that here as well, x transpose x transpose inverse. Okay, and there you go, you get this. Now in a locally weighted regression, what will happen is you will have the W thing come into picture, that's all. Okay, and that's exactly what we have. Okay, x transpose, instead of having x transpose x inverse times x transpose y, you will have, you know, so basically you will have an additional weight vector component in your, it's actually x theta equal to y, and so everything will change. Probably let me do this in a fresh way. I mean, let's just do it here. So x theta equal to y, and so therefore x transpose x theta equal to x transpose y, and therefore theta is nothing but x transpose y, and then you got to multiply it by the inverse of, because x transpose x on the right, x transpose x on the right. Okay, and that will get you your parameter estimations. Okay, and so this is known as a pseudo inverse operator. So what you do in a locally weighted regression is the following. Is your theta is x transpose wy times, I mean, it's very simple, right? Your x transpose wx inverse times x transpose wy. Okay, so you just add this weight component, that's all. Okay, so without a mathematical proof, we just show this, but the whole idea is that we use a hyperparameter in addition to the parameter estimation. That's about it. So it's like it's not a model sensitive learning, it's a parameter sensitive learning. Okay, so this brings us to the end of locally weighted regression. Thank you.